Welcome, digit recognition specialists, to a fascinating journey in our machine learning series. I'm thrilled to be here with you, and today we're diving into a classification task using a classic dataset and a powerful explainability tool. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we classify handwritten digits. Let's get started by setting up our environment and gathering our tools for this pixel-based adventure. I begin by installing the required libraries in Colab with pip3 install interpretLime. These libraries are key for explainable AI, helping us understand our model's decisions. Next, I import the essentials: NumPy for numerical operations, pandas for data manipulation, and sklern's load_digits to access our dataset. From sklern, I also bring in train test split to split our data, random forest classifier for our model, and accuracy_score and classification_report to evaluate performance. From interpret, I import LimeTabular from the black box module, our tool for local explanations, along with the show function to display results. I set up inline visualizations with setVisualizeProvider and inlineProvider, ensuring our plots render directly in Colab. I also set a random seed with np.random.seed42 for reproducibility. With our toolkit ready, let's load the data. I load the digits dataset using sklern's load_digits function. This dataset contains 1797 samples of handwritten digits, 0 to 9, each represented as an 8 by 8 pixel image, flattened into 64 features, pixel intensities from 0 to 16. I create a data frame with meaningful feature names, labeling each pixel as pixel_pixel_0 for the top left pixel, pixel_7_7 for the bottom right, and add the target column, where the value is the digit 0 to 9. I print data.head to take a look. The first row shows pixel_0_0.0, pixel_0_25.0, pixel_7_313.0, target 0, digit 0. The next row has pixel_0_312.0, pixel_7_416.0, target 1, a digit 1. Since LimeTabular supports only binary classification, I filter the dataset to include only digits 0 and 1, creating data_binary with 360 samples, 182 digit 0, 178 digit 1. I ensure the target is mapped to 0 and 1, keeping it binary. Let's prepare the data for modeling. I split the filtered dataset into features, and target X is all columns except target, the 64 pixel features, and Y is the target, 0 for digit 0, 1 for digit 1. I use train test split to allocate 20% for testing and 80% for training, with random state 42 giving us 288 training samples and 72 test samples, roughly 35 digit 0 and 37 digit 1 in the test set, based on the balanced subset. The features are all numeric, representing pixel intensities, and there are no missing values, so we're ready to train our model. I initialize a random forest classifier from sklern with n_estimators equals 100 and random_state 42. Random forest classification is an ensemble method that builds multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It aggregates their predictions through majority voting to classify outcomes, reducing overfitting and improving accuracy, making it ideal for classification tasks like digit recognition, where pixel patterns may have complex relationships with the target. I call fit on xtrain and ytrain to train the model, letting it learn how pixel intensities distinguish digit 0 from digit 1. Once trained, I make predictions on xtest with predict, storing them in ypred, and evaluate with accuracy and classification_report. The results are perfect. Accuracy score 1 to 100% correct predictions, 72 out of 72 samples. The classification report confirms for digit_0, precision, recall, and F1 score are all 1.00, support 35. For a digit_1, all metrics are 1.00, support 37. Macro and weighted averages are 1.00 across the board. a flawless performance on this binary task. I use LimeTabular from Interpret's black box module to explain our model's predictions. LimeTabular is an explainability tool based on Lime, local interpretable model agnostic explanations, which provides local explanations for any model. In our case, a black box random forest. It works by perturbing the input data around a specific instance, fitting a simple interpretable model, like linear regression, to approximate the black box model's behavior locally, and then showing how each feature contributes to the prediction. I initialize LimeTabular with rf_model.predict_proba to get probability outputs, xtrain as the background data, the feature names from x.columns, and specify all features as continuous with feature_types. I generate a local explanation for the first test sample with lime.explainLocal on xtest.ilog0 and ytest.ilog0, named lime local explanation. I extract the explanation data with local explanation.data 0 and print the details. Predicted 1, digit 1, true label 1, digit 1. Correct. Feature contributions show pixel_4_4 at 0.2411. The strongest positive push toward digit 1, indicating a high intensity in this pixel. Pixel_3_4 at 0.1790. Pixel_4_6 at 0.0980, and Pixel_3_6 at 0.0759 also push toward digit 1, focusing on the central right region of the 8x8 grid. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The Pixel_4_4 bar stretches right in orange at 0.2411, driving the digit 1 prediction, likely a bright spot typical of digit 1's vertical stroke. Pixel_3_4 and Pixel_4_6, also in orange, add 0.1790 and 0.0980, reinforcing the pattern. Smaller bars like Pixel_5_2 at 0.0451 show other contributions, with a final prediction of 1 marked at the top, a clear breakdown of how pixels shape this digit classification. To wrap up this digit recognition journey, we've analyzed the digits dataset, filtered to 360 samples of digits 0 and 1, and trained a random forest classifier, achieving a perfect accuracy of 1.0000 and F1 scores of 1.00 for both classes. The local explanation via LimeTabular revealed key pixels like Pixel_4_4 and Pixel_3_4, driving a correct digit 1 prediction, offering a clear view into our model's reasoning. Random forest classification's ensemble approach captured intricate pixel patterns, and LimeTabular's Lime-based method provided transparency for our black box model in this binary classification task. Grab this code, experiment with other digit pairs, and dive deeper into digit recognition. I'm amazed by this pixel-perfect analysis. Hope it's got you thinking about data's role in pattern recognition. See you next time for another insightful data exploration.